So you have had a lot of practice in finding Laplace transforms and inverse Laplace transforms. And, you know, okay, that's nice. We know how to find Laplace transforms and inverse Laplace transforms, but how is that going to help us solve differential equations? Well, here's an example of a second order differential equation. So this would correspond to a mass spring system with a driving force given by e to the negative 4t power. And we want to solve this differential equation. The y of 0 equals 1. Okay, so initially the mass would be 1. It would be, it would be, let's see. Well, it would have position 1, and y prime of 0 equals 5. So that means the velocity is going downward. And the mass is 1 unit below the equilibrium. So, of course, we could use the techniques that you learned back in section 4.4 to solve this differential equation. We could use the method of undetermined coefficients, but now we're going to use Laplace transforms. So let me give you a moment to copy this down, and then we'll go over the solution. Okay, so let me bring up the ebook real quick. Okay, so I'm bringing up the ebook class just to, let's refresh ourselves on some rules for the Laplace transform of a derivative. So the Laplace transform of f prime of t is equal to s times the, hold on here, this is the, yeah, that's the one I want. Yeah, the Laplace transform of a derivative of a function is equal to s times the Laplace transform of that function minus f of 0. Okay, and the Laplace transform of a second derivative of a function is equal to, actually, hold on here, I got the wrong thing highlighted. I want this highlighted. Good, that'll work. Hold on. Yep, that's good. The Laplace transform of a second derivative of a function is equal to s squared times the Laplace transform of the function, that's denoted by big F of s, minus s times the function evaluated at 0 minus f prime of 0. And of course, we can find the Laplace transform of a third derivative and a fourth derivative, and in fact, you know, there's a pattern here. There's a pattern. and they give the general formula for the Laplace transform of the nth derivative of a function with respect to t. So, all right, of course, we're going to have to use the Laplace transform of a first and a second derivative. We'll have to use those formulas. So let's see now how are we going to make use of this? Why did we learn all these Laplace transforms? Okay, well, let's get to the solution here. So what I'm going to do is the following. Okay, of course, I always have my table of Laplace transforms handy, right? But let's get to the solution here. So in the solution, okay, and that's what this is here. This is a solution. Okay, example, it's a solution to an example, but solution. So what I'm going to do is I'm going to write the differential equation in terms of Leibniz notation. And do we agree that this left-hand side, y double prime minus 3y prime plus 2y, is that a function of t, class? Is that a function of t?
Yes, it's a function of t.
Yes, it's a function of t. After all, y is a function of t. So therefore, y prime, thank you, Michael, and y prime is a function of t, therefore. And so since y is a function of t, y prime is a function of t, the first derivative is a function of t, and a second derivative is the derivative of the first derivative. So it's a function of t as well. So what I'm going to do is I'm going to take the Laplace transform. Hold on here. I'm going to take the Laplace transform of the left-hand side, and then that's going to equal the Laplace transform of the right-hand side. And I'll write it in just a little bit nicer here. So in the differential equation, here, you have really think of it like you have a function on the left equaling a function of t on the left equals a function of t on the right. So if I take the Laplace transform of the function on the left, that then has to equal the Laplace transform of the function on the right. Well, on the left-hand side, the Laplace transform of a difference of functions is the difference of the Laplace transform. So think of it like this. The Laplace transform of a sum of functions is the sum then of the Laplace transforms. Okay. All right, so I'm right down here to the third step. Please let me know if anybody has a question. If anybody has a question, please let me know. All right, Christopher's good. Excellent, excellent. All right. So what we're going to do now, is, well, we have to apply some rules. So for instance, the Laplace transform of a second derivative is equal to, well, the Laplace transform of the second derivative of y of function y is equal to s squared times the Laplace transform of that function y minus s times y of 0 minus y prime of 0. And the Laplace transform for the, hold on here, the Laplace transform for the derivative of y is equal to s times the Laplace transform of y minus y of 0. And then finally, the Laplace transform of y is the Laplace transform of y, and we denote that by the capital Y of s. So the Laplace transform of y, writing it in the notation capital Y of s, just makes it's a little easier to write. Okay, a little easier to write. And then finally, the Laplace transform of e to the negative 4t by virtue of our Laplace transforms rules, that's going to equal 1 over s minus negative 4, right? 1 over s minus negative 4. But what is s minus negative 4? That's s plus 4. And so this gets us then down to this step here. All right, are there any questions so far? All right, well, let us continue then. Let us continue. So, all right, let me just kind of, I like to kind of write things and then clear them out. And then, you know, it's always in the recording, right? So the y of 0 equals 5. That was one of our initial conditions. And the y, this is a y prime, right? Hold on here. I want to make sure I write everything very nicely. That's a y prime. So a y prime, the initial condition on y prime was y prime of 0 is equal to, hold on, wait. I have a little mistake here. Hold on. Let me do it again. All right, so y of 0 was equal to 1. That was an initial condition in the problem. And y prime of 0 was equal to 5. Okay, that was the second initial condition. Second order differential equation, to solve it, you need two initial conditions, right? So you see how nicely with Laplace transforms, how these initial conditions, they just fit right into the problem. Now what I do is on the, I'm gonna distribute the 3 here. 3 times s times y of s and 3 times 1. Okay, and then I'm going to simplify the left-hand side. I'm going to, the negative 5 and the 3 combine to give you negative 2. All right, I'm just going to, simplify the left side. And what I want to do is group together all the terms that have that Laplace transform connected to them, the big y of s function there. And what I do is I factor out that big Y of s function. I factor out that Laplace transform. So always remember that hold on here, that this Y of s stands for the Laplace transform of y. And we know y is a function of t. One moment. I want to clamp put a clip on this problem so that I have it, because, okay, I got it. One moment here. Yes. Okay, let me see. There were a few questions here. In orange, that's a 5, Zachary. This is a 5. This is a 5. That's a 5. All right, so let me give you a moment to catch up here. All right, before we continue, and please let me know if you have any questions. All right. So looking here at this last equation, what do you think we're going to do next? What do you think the next step is?
Because we want to get the function y, we have to take the inverse Laplace transform of y of x.
So you're right, Michael, that we're going to be bringing in the inverse Laplace transform, but
but we need to divide by
good.
S squared minus 3s plus 2.
That's correct.
On both
We
sides.
want to.
Then
that's exactly right, Michael. So we want to find out. We want to say the Laplace transform of y equals some function of s. And so we have to divide through the entire equation by s squared minus 3s plus 2. Now, what will happen then is, well, let's do that. Okay, let's do that. So I can go to the next page, or may I go to the next page? Are there any questions? Maybe give me a thumbs up if you're ready to go to the next page. All right, Max is good. Christopher's ready. Does anybody need any more time to copy? Okay. Okay. Well, so we're going to divide through this equation by s squared minus 3s plus 2. Okay. And that's what we do. So the Laplace transform, which I denote by y of s, equals then s plus 2 over s squared minus 3s plus 2 plus 1 over s plus 4 times s squared minus 3s plus 2. Now we have two fractions here. We have two fractions, and we can combine the two fractions. Okay, we can combine them if we multiply the first fraction by s plus 4 over s plus 4. The least common denominator between the two fractions is s plus 4 times s squared minus 3s plus 2. And so that gets us here. And if I FOIL s plus 2 times s plus 4, if I FOIL this here, that's just s squared plus 6s plus 8 Okay, and so my Laplace transform will be equal to s squared plus 6s plus 9 divided by the denominator s squared minus 3s plus 2 times s plus 4. This is what I have. Now, of course, I'm going to factor the bottom. And remember what we're interested in finding, okay? So I mean, again, this is the Laplace transform of y. But what are we interested in finding? What do we want to find here? Ultimately, in the end, we want to find what?
Y.
Right, we want to find y. That's right, Michael. That's right, Mark. So to get y, okay, whatever, you know, whatever y is, I know that, you know, I'm going to have to take the inverse Laplace transform of the Laplace transform of y. And the Laplace transform of y, of course, is that denoted by big Y of s. Right? That's what I have here, right? So that means then that, well, I have to rewrite the right-hand side of, I have to rewrite the right-hand side. So how am I going to rewrite this right-hand side so that I'll be able ultimately to take inverse Laplace transforms? What approach do we have to use? To rewrite this? Right-hand side. To expand it out. What's it called? You did it in your homework. Partial fraction expansion. That's right. That's right. Okay, and so that's what we need to do. And I want to mention too, class, just something I was thinking about in regards to the exam. You know, section, like whenever you have to do a partial fraction expansion, like for instance, a section 7.2 problem. Okay, I do want to see the work in that. I don't want to just see this is a partial fraction expansion with an answer. I want to see it worked out. Okay, so just keep that in mind. And let me show you how we'll work this out. Now, you've seen several approaches for I want to see that you understand the concepts, right? And that's why I want to see things worked out. So here, what I do is I have three linear factors. So, here we go. That fraction is going to equal a over s minus 2 plus b over s minus 1 plus c over s plus 4. Then what I want to do is I'm going to multiply both sides of this rational equation by the least common denominator, which is s minus 2 times s minus 1 times s plus 4. Okay. Whoops, that's an s minus 2. Hold on. Okay, there are the three factors. And of course, on the left side, we have simplification. So on the left-hand side of the equation now, we have s squared plus 6s plus 9 on the left side. And then on the right side, we're going to have what you see here. Okay. So like, for instance, the first, how do we get a times s minus 1 times s plus 4? Well, a over s minus 2 times the s minus 2 times s minus 1 times s plus 4, the s minus 2 simplify out. Okay, and now I could expand this whole right side. As a matter of fact, in the examples that we did on, or example maybe that we did on Tuesday, I had a partial fraction expansion where I expanded the right-hand side out, and then we equated terms, and we were able to solve for, our A, B, C, D, whatever, right? But there's a second approach that you can use for partial fraction expansion. You can pick different values of s. Okay, so like, and then solve for the values A, B, and C that way. So like, for instance, I pick s equals 1. Now, why am I going to substitute s equals 1? Why am I going to substitute s equals 1 in? Why do I pick s equals 1 as an s value? Why not pick like s equals 7? Why pick s equals 1?
Cancel out two of the terms.
That's exactly right. That's exactly right, Justin. When I put s equals 1 in this equation here, this term will drop out, and the last term will drop out. And so when I put s equals 1 in, I'm going to get 1 squared plus 6 times 1 plus 9. That gets me 16. And that will equal then b times negative 1 times 5. The 1 comes from, let me see here, hold on. Put it in red here. So the 1 here comes from the 1 minus 2 here. And the 5 comes from 1 plus 4. S plus 4. When s is 1, 1 plus 4. And then 16 comes from 1 squared plus 6 times 1 plus 9. Okay, that gets you 16. And so we determine that b equals negative 16/5. Then I pick s equals negative 4. That, again, that's another nice value. S equals negative 4 means in this equation here on the right-hand side, well, which terms would drop out if s equals negative 4 on the right-hand side? You got first, second, third terms. When s equals negative 4, which terms drop out here on the right side? Well, of course, on the left side, I get a 1. And obviously, the first two terms drop out. Okay, and you're left with c times negative 6 times negative 5, so c equals 1/30. I know some of you are copying, and so I want to. And then finally, I let s equals 2. How many like this way of doing partial fraction expansion, finding the coefficients?
It definitely saves some time.
Okay, all right. Justin likes this way. Okay, very good. Let's see. Hugh Young said, "Now you can solve for b." That's right, Hugh Young. Yeah. We solved for b, and all right. And well, and sometimes what happens is, like in the homework, you had a problem where if you did it this way, you had an A, B, C, and D, and you could solve for A and B. But then to get C and D, you'd have to substitute. You could substitute a couple more S values in the equation, and then get two equations with two variables and solve for the two variables. I mean, so I think a lot of people, I don't know, people vary in terms of what they like. But all right, are there any questions? All right, are we done copying this page? May I go to the next page? All right, Christopher's good. So naturally, I'm going to put in the values A, B, and C, okay, here. All right, I'd like maybe a few more thumbs up before I move forward.
Yeah, I'm good.
You're good, Justin and Max? So, okay, well then, all right, Andrea, thank you. So, okay, so now our Laplace transform is equal to, 25/6, that was A, over the S minus 2, minus 16 fifths, that was B. That goes over the factor S minus 1. And then plus C is 1/30. That goes over S plus 4. So now we got a much nicer looking Laplace transform. Absolutely beautiful what we're doing here. Absolutely amazing. All right. Now, one thing I'll comment on in terms of notation here, I have really shouldn't have parentheses here. I'm doing an inverse Laplace transform of my Laplace transform, so I should have brackets here. So please make that correction. These should be brackets. Man, they should all be brackets, shouldn't they? All right, well, that's all right. We'll do that. I can do that. All right, and so now, well, using your table of Laplace transforms, you know the Laplace transform. Well, you know that the Laplace transform of e to the t is equal to 1 over s minus 2. So the inverse Laplace transform of 1 over s minus 2 is e to the 2t. Okay, similarly, you know the Laplace transform of e to the 1t is 1 over s minus 1. Well, therefore, the inverse Laplace transform of 1 over s minus 1 is e to the t. And finally, the Laplace transform of e to the negative 4t is 1 over s plus 4. So the inverse Laplace transform of 1 over s plus 4 is equal to e to the negative 4t. And so now you've come up, you have your solution. You have your solution to this differential equation. We found it. Okay, put a nice smiley face there, right? Yay, we got it. So, so now, I mean, now you have a new approach. You have, yet another way to solve a differential equation. You have another way to solve an initial value problem. You can use the Laplace transform approach. How many like this approach?
It's not bad.
Yeah, it's not bad. It's not bad. Justin likes it. Zachary likes it. Christopher likes it. Christopher thinks it's an okay alternative. Sure. And I'll tell you when our, well, Paige, what will happen is for your final exam, it will matter because but I guess I'm glad you asked that question. Paige is saying, does it matter which one we use? So if you're solving a second order differential equation for a mass spring system, you've learned multiple approaches. Which one do you use? So I'll have to, I would have to, if I don't say anything, you could use, any approach. But of course, if I said use this approach, you would want to use this approach. And certainly also remember well, yes, good question, Paige. Paige, you now have something to think about, something more to think about, but that's good. All right, I like good questions. All right, are there any other questions here? Okay. I'll stop the recording.